Thank you, Georgi, and ladies and gentlemen. Allow me to present this very nice thing that is now implemented in the Model Code 2010. That there are some safety formats that are applicable for nonlinear analysis. That means engineers finally, let's say, have some guidance how to use nonlinear analysis in some safety framework. So I will first start by showing some examples of various classes of application of nonlinear analysis for serviceability, ultimate limit states, and also some structural detailing of structural elements. Then mention a little bit, very briefly, some main aspects of the material models, their validation, and then I will show the 4 safety formats that are available in the model code and applicable for nonlinear analysis. So one first example comes from a university which is in northern Italy. It is a very modern design, and nonlinear analysis there was to check the serviceability limit, mainly to check the cracking and deflections. As you can see, this university is a very slender structure. A lot of concrete elements are left visible, and it is a pre-stressed. There are pre-stressed concrete elements. So that was, for instance, this case. You see these are columns and beams. This joint is very, very much visible, left open to the exterior, and it is at the same time very slender, and it was pre-stressed. So here you see the normal reinforcement. Here are some dimensions, and here are the pre-stressing cables. And the objective of the nonlinear analysis here was to verify the crack width in these regions so that the cracks are not visible to the public. Of course, people might be afraid walking in the university and seeing large cracks. So here are some parts of the 3D model, the deflections, and more important, the crack widths calculated by the software using the crack band method, which I'll mention later on. Of course, it's always important to make certain validations when using nonlinear analysis. One of the nice validations or comparison is, of course, to check by 2D and 3D models. And in addition to the serviceability limit states, also the ultimate limit states can be checked and was checked by nonlinear analysis. Also, in many, what was in this case investigated, making some kind of parametric study, what will be the ductility in these regions. Because, of course, the model that we are using is a 3D model for concrete, which considers the triaxial state of stress, also the confinement. But on the other hand, when it comes to modeling of concrete after reaching the peak, the experimental evidence is very limited. So we investigated various situations when the concrete is very plastic, and then the situation when the concrete is very, very brittle. And here you see the various calculated load displacement curves. And when checking the ultimate limit state, we need this global approach, which I will come to that later, where we increase the load up to failure, and then of course we need to check the load, the reached peak loads with respect to the level of the design load. And of course, up to now, the engineers were, so to speak, left in the open air. What should be the safety factor that they should consider? And this is where the model code now is very, very useful tool, because it finally provides some rules and some guidance in this direction. Also, another aspect of this building was that there were no expansion joints. So also, let's say, larger scale model was created of the quarter of a half of one of the story, including, of course, some supports, loads. In this case, what was very important was the shrinkage and thermal strains, expansions. Here is some detail of the model around the elevator shaft, and of course reinforcement model near the columns. And here you see some results. This shows the displacements from the permanent load, and then when it comes to the thermal load, you nicely see, due to the shrinkage and temperature, you see how the crack develops between the fields and also near the columns. And here is the picture of the reinforcement, stresses in the reinforcement, and more important also here we see the development of the crack width in the middle of the span. So this shows the crack width along with the deformed shape. So that was, let's say, a building where we were checking the service limit states as well as the ultimate limit state. And now I am showing another example, which is a bridge, or it's almost a viaduct. It's near Prague. You see, it's a very nice structure with very slender columns. And the objective here was to use nonlinear analysis to verify some of the construction stages during the analysis, because you see the piers are very slender. Of course, once the bridge is or the viaduct is fully connected, it becomes a very stable structure. But during the construction, there were some concerns about the stability. So first they placed these temporary stiffeners in the middle of the piers. And the bridge or this viaduct was built by a cantilever method. So you see here one of the cantilevers at the point where it was almost completed. And now something about the model that we used. So here is a model of this cantilever segment, or part of this bridge. Foundation, including the piles. These are the slender piers. To model them, we used shell elements. They look 3D, but actually by geometry they are displayed as 3D, but internally they are calculated as shell elements. Of course, to model such a large-scale problem, it is not possible to use solid elements for the whole structure, so it is important to make use of some of the more efficient element formulations like the shell elements or plate elements. So this shows the box of the bridge. This shows the individual segments as they were. This also shows the construction process, because these segments were always built gradually, and also gradually pre-stressing tendons along the top surface were activated or also applied. Now coming to this verification by nonlinear analysis, it is a little bit different from the classical approach, because we have the various load cases, which in this case, this is, for instance, the wind load causing suction and pressure on one side and suction on the other side, wind acting from one side, of course, longitudinal wind, and so on. So various cases were considered. And here are some results of the stresses and stresses in the cable. And now in one load case, this was the final failure mode by some plastic hinge or compressive failure at the bottom of the bridge girder. So this is one of these load cases, which was the main one, the most critical one. and I will come to a summarizing table. But this load case was the load case where we were checking the weight, or the load case of the weight from the concreting vehicle. And this is, again, this typical evaluation I told you. So in this global assessment, what it means that for each load case, basically this kind of separate verification needs to be performed. So it is, of course, more demanding than classical linear analysis, where we can use with advantage the superposition of load cases and also superposition of calculated internal forces. In nonlinear analysis, it is necessary to check each load case separately. So usually it would be done for some critical structures and for the most critical load cases. So now what should be, in this case, you see the safety factor was about 1.7. And well, later on, we'll come to the safety factors which now are available in the model code for the practical applications. So as you see here, here is a summary of some of the load cases that we were looking at for this case. Wind, you see very large load factor for failure. Casting vehicle alone, but if we then consider all the loads acting together, this was the load factor, which was 1.7, which was not that large. On the other hand, this was a construction situation where it is quite easy to control very well the loading acting on the structure. One last example before going into these theoretical aspects is containment structure, nuclear containment. This comes from a project in Finland. I think this is the only containment which has been recently completed in Europe, only nuclear power plant. Here you see the geometry of the containment. It's a double wall containment. The interior wall is pre-stressed, the outer wall is not pre-stressed. So the interior wall is pre-stressed. It is supposed to protect the neighborhood from any accidents happening inside the reactor, and the outer building is more for protection against outer actions, for instance, plane crashing to the containment. Now something a little bit about the model. So this is the half or section through the finite element model. There you see the total model. There are some openings in the building. And this model consists of various elements, again, as I have shown you already for that bridge. So the wall is, the containment wall is modeled by shell elements, the ribs and the foundation by solid elements, and then inside the containment there is a steel liner, which is modeled by membrane elements. This is the description of the plate elements. So what we like to use is the plate elements or shell elements, which are actually 3D elements. Internally, they are formulated as a shell element, but they have displacement degrees of freedom only. And this then makes it very easy to connect such an element with volumetric elements, for instance, for the ribs or for the foundation. So in this way, one can easily use bending elements, that means shell elements, in the areas where bending should be important, but in the areas where we want to capture shear failure, there we can use solid elements. There is the ring beam, but this only shows the wall. So this was shown a little bit on the previous slide here. You see that the ring was by solid elements. Yes. Ring beam is solid elements. Yes. Yeah, here it is actually attached from the between. So here are solid elements which are attached to a shell elements on the inner surface. And then farther on, there is additional layer of these membrane elements to model the steel liner. Very important in these structures are the pre-stressing cables. You see, very detailed. It is important to have a quite good representation of these pre-stressing tendons, because in the end, the failure is usually local failure. So any deviation of the pre-stressing tendons can have an important effect. Now, what is, I think, important when applying nonlinear analysis to reinforced concrete structures or pre-stressed structure like this one, it is very important to have a good representation of the reinforcement and good representation of the solid model. We are using the well-known, and I think most softwares are using the well-accepted embedded approach, in which it is then easy to define the reinforcement totally independently from the 3D model, and then later on, when the finite element mesh is created, the reinforcement is then separated into small truss elements, which are then embedded into the solid finite element model. In this way, very complicated reinforcement shapes can be, reinforcement detailing can be modeled. And in addition, this approach allows you to introduce here at these nodes that belong to the reinforcement additional degrees of freedom to model the slip. And that means a bond slip law can be easily introduced. What is in pre-stressed concrete? Of course, pre-stressing losses are important to consider. Of course, there are some nonlinear techniques also that you can calculate the pre-stressing losses, but that means that each tendon should be pre-stressed one by one, also following the pre-stressing procedure, which might be quite complicated. So actually, in this case, what was done was that the theoretical pre-stressing losses were directly applied along each tendon as initial strains. This shows the final failure mode. Of course, this structure is a concrete structure, but in the end, you can think about it as a steel structure, because what in the end very much decides is the tendon yielding. So this is the final yielding of tendons. This is the cracking of the concrete wall. And here you see the blown up, of course, increased deformation. I forgot to mention the main loading case in this situation is, of course, some temperature loads, but then there is an overpressure which is gradually increasing, internal pressure. And so this global check was by increasing the internal pressure following the deflections, and then we reached some final failure mode, which is very much, actually was very much controlled by the tendon yielding, and you see the safety factor, which was about 3.5. And in various containments that we analyzed, it was always around 3, the safety factor obtained. So which I think is good. Now, nonlinear analysis actually in most situations is used up to now to checking details. To check the whole structure is nice, but it is demanding. On the other hand, when you model the whole structure, the problem is that then the model of various details is maybe too coarse. But on the other hand, usually details decide about the problems or the structural situations. So this is so far, I would say, not feasible to have the whole model of the whole structure and at the same time model each structural detail that might be critical. So I just now will go through some details also where nonlinear analysis is used. So in case of this containment, typical detail is either the buckling of the liner, and this buckling of the liner, of course, then brings the problem of anchoring the liner into the concrete. So this shows a typical situation how the liner is usually anchored. There are some studs, and at the same time there are some I-shaped or L-shaped steel elements to which the liner is welded. So, and the load case scenario for such an anchorage is again, main loading scenario here is an accident. It's called local loss of coolant accident, which introduces, first of all, pressure, but at the same time, higher temperature. The higher temperature will heat up the liner, and the liner will buckle up. Once it buckles, it will introduce non-uniform loading on the anchor, and then this may result in some cracking and some failure mode. And then nonlinear analysis could be used to calculate this load displacement behavior of these anchorages. This is an example of the buckling of the liner. That's because one of the important design criterions in the containments is that the strain in the liner should not exceed certain values. Problem is that such an evaluation is very, I would say, old-fashioned, because the strains could be very large if you think about some details, connection of the liner to these anchorages. So when checking by nonlinear analysis, the strains will be whatever size whatever value you want, depending on the finite element size that you select. Also we participated in a round-robin analysis, which is now being organized here in India, in Baba Atomic Research Center. They built this containment, which is a 1-to-4 model, and they are now organizing some round-robin analysis of this. But as far as I know, they have not yet, their idea is to bring it up to failure. But this so far has not been achieved, and I think Dr. Joklekar had some presentation about that during the conference. 1.56, yes. Yes, yes. Yes, they put some liner inside some. Okay. Yeah, so we predicted the failure, which you see here at about this pressure, but so far it has not been verified. So now going to a little bit about the material models and theory. There are various commercial softwares. I would say I listed here 3, which I would say contain the most sophisticated concrete models, but of course there are many others. So when using nonlinear analysis, the typical situation is that most softwares introduce some advanced material models, which then always divide the nonlinear analysis into a incremental and iterative process. In each increment there are iterations. First there is an elastic predictor assuming elastic behavior, and then the stresses throughout the structure are checked with respect to the criteria and are reduced by calculating the proper stresses in the material, and then by integrating them we come up with some internal forces, and then this difference between the internal forces and applied forces introduces some residuals, which are then iteratively redistributed throughout the model. What is important when modeling concrete structures is to, let's say, cover these effects: concrete cracking, confinement, shrinkage, creep, reinforcement, yielding of reinforcement, hardening of reinforcement, and of course rupture of reinforcement. Important is bond, modeling of loss of bond between reinforcement and concrete. And of course some contact problems can be an issue because various materials may be used in our structure, and the interface properties should be addressed. While going to the material model itself for concrete, typically most of the material models work along the line of the strain decomposition. That means that the strain tensor is decomposed into elastic part, plastic part, and fracturing part. Fracturing part usually addresses the cracking. Plastic part usually resolves in the steel, the plastic behavior, and in the concrete, the compressive crushing of concrete. Regarding modeling cracks, which is an important part because the cracks always occur even under serviceability situation. Of course, when it comes to ultimate limit states, there the compressive failure or reinforcement yielding or reinforcement rupturing becomes the dominant mechanism. What I'm showing here is one of the main models which is up to now used by most softwares to model the cracking. This is the so-called smeared crack model where it is assumed that the crack, which in a real situation is a single line, is somehow smeared over the element. And then this kind of simple equation is used to translate the strains, which we usually have as our kind of a driving parameter inside each finite element, to translate these strains into crack opening displacements. And then we can go to the softening law for concrete, and in this way we can properly take into account the energy dissipation during the cracking process. The important parameter in this formula is the size of the crack band. In ideal situation, we can assume that inside an element there will be one crack. And then we can say that this crack band size is the size of the element perpendicular to the crack direction. This is a good approach. It is also, I think, important that this crack band is calculated on the element level. In some softwares, it is an input parameter. But then it means that you should use finite element sizes which are more or less square and uniform all over your model, which in many situations is a very restrictive condition. The other issue we have to keep in mind that if you come to reinforced concrete and if you use large elements, let's say you model the containment, there the element size maybe is 1 meter, and it's reinforced, then this assumption that there is a single crack inside one finite element is not true anymore. So this also should be somehow addressed by the software, that once it is reinforced, then we need to make this equation a little bit more complicated. Well, what this equation means, finally it means that when we have the localization of crack, that it localizes into a single element, which I told you in heavily reinforced structures and when using large elements may not be true, because in reality there may be more than one crack inside the finite element. But this is this assumption, and good method how to address this, as I have already mentioned, is this crack bend approach. The good thing is that it can then capture also the size effect. So nonlinear analysis will automatically take into account the size effect of your structure, at least the energetic size effect. Sometimes there is also a statistical size effect, so this one, of course, cannot be addressed by this model, but the energetic size effect can be very well captured. Now a few validation examples. A typical validation example is to model the tension stiffening, which is a typical or classical situation, bar embedded in concrete. If you pull it, you will obtain this kind of behavior. Finally, there is the yielding. Finally, the response is given by the yielding of the bar. And this part we can consider tension stiffening, some additional stiffness of cracked concrete. And it is, of course, also affected by the bond behavior. And what I would like to show with this example is that this tangent stiffening effect, also the bond effect, can be addressed without any need of a special bond model or special stiffening model if sufficiently finite elements are used, because all these effects actually could be very nicely represented by suitable model for cracking of concrete. But again, if we come to modeling large structures with large elements, lot of reinforcement, then you cannot use such a fine mesh around each reinforcement. Then bond models or tangent stiffening models are useful. Also, the proper modeling of concrete cracking can very nicely represent crack spacing and crack width, which is shown on this example. And when modeling 3D structures, what is important is to consider the 3D state of stress. The typical triaxial failure for concrete has already been shown here in this morning. And while of course, these criteria can be easily incorporated into any finite element solution and then obtain the confinement effect. So, when validating numerical models, one should divide it into 3, let's say, levels. First thing is to be able to reproduce material tests. That is compression test, tension test, triaxial tests. Then there always will be, when modeling with finite elements, there will be an issue of mesh sensitivity. So every engineer using nonlinear analysis when modeling some structure, certain structure, should make some sensitivity study. Should at least use 2-3 models to evaluate the mesh sensitivity of his model. And then what we are proposing and should be also the solution to the model uncertainty, because each software is using certain models. It is very difficult to provide any general guidance to this model development. So the only way how engineers can obtain some, let's say, some confidence in the model or software they are using is to simulate some benchmark problems, to simulate some shear problems, and in this way get the feeling how the software behaves in for these types of problems. Yeah, I'm showing some benchmark where we recently participated, just to give you an idea what I mean by these benchmarks. This was experiments which were performed in Zurich by Professor Marti. He simulated these kind of slabs in shear with different geometries, different reinforcement arrangements. And here you see some results from this benchmark. Each box corresponds to one participant, and the horizontal axis is an error in displacement. On the vertical axis is the error in strength prediction. And each point then corresponds to one specimen arrangement. So, and that you see that it is, even for these relatively simple problems, still it is not so easy to predict, to obtain good prediction. Actually, the winner of this competition was Professor Kollegger. These are his predictions. Mainly, he was announced to be a winner because his predictions from engineering point of view are a little bit underestimating the strength and overestimating the deflections. From engineering point of view, it's a good prediction. But on the other hand, we should say that he used an approach by hand, more or less, yes? So for these simple problems, it is quite clear that the engineering knowledge is here from experiments, so it is, of course, the hand calculations very often give very good results. also he was in the same group as these people which are in his group, and they did analysis by using Athena, our software. Well, why we like to show it is that these people, they did not communicate with us. They did it totally independently, and they obtained quite good predictions, mainly in terms of strength. Our predictions had the best predictions in terms of strength, but we a little bit underestimated the displacements. But actually, what was the case? We underestimated the ductility. So which on the other hand, you may say, is actually also on the safe side. Because what happened, that these experiments were quite ductile, and we predicted quite brittle failure. Another benchmark comes from
predicting the ductile behavior.
Mm-hmm.
Did you use the actual stress curves of displacement speed or the theoretical stress curves which are given in the code? Because they could be quite different.
Well, there was no pre-stressing. Just you said pre-stressing, but this is not pre-stressed. This is reinforced. Yeah. But I must say I don't remember now. I think we used something between. Yeah, we used some hardening bilinear model for steel, and hardening was based on the experimental data they provided. The problem here is the compressive behavior, because then it's a shear problem, so it is very much dominated by crushing of concrete. And if you use too brittle, let's say, softening behavior for concrete in compression, that was the main problem here for our analysis. And it's also shown here. This is another benchmark from France, organized recently by this project GEOS, or SEOS, I think it's called. SEOS, yes. So one example was this wall. Here you see the experimental response, and here you see the numerical result for 2D, 3D. But of course, again, if I told you, like in the previous case, if we use, let's say, the default settings which are in our program to make sure that the engineers get behavior on the safe side, and these behaviors little bit underestimate the ductility of the compression failure, then you obtain lower peaks. So for 2D, it is quite natural that to have a 2D model of the confinement region, it really needs to be in the model. It cannot be calculated automatically. But the 3D models should capture the confinement of this crushing region. So now coming to these global models, global safety formats. So if we just rephrase what is the current approach. Currently, when making design or checking the structures, we apply forces to our structures, and then we calculate the internal forces in some critical sections, and that at each critical section we check if the actions are design actions, including, of course, all the partial safety factors on the load side, if they are smaller than the resistance of the section, which again includes all the partial safety factors for the sectional behavior. So now when this is not very suitable, such an approach, for nonlinear analysis. So for nonlinear analysis, it is better to apply the loads on the structure, keep increasing them until the failure, actually and then we calculate the resistance, not of the section, but the resistance of the structure with respect to the given set of loads. And then we will compare that to the load level. So this is in a sense, more correct approach because it eliminates the discrepancy in this classical approach. Because in this classical approach, what is usually happening is that to calculate the forces, we use linear analysis. But then to calculate these resistances, we assumed highly nonlinear behavior, so which is a little bit discrepancy here. So this discrepancy is eliminated in this approach, but of course at some additional cost because we cannot use the superposition, and also the analyses are more demanding. So this is the basic design condition we have. And now how do we calculate this design resistance? Now in the FIB model code there are three possible approaches. First one is, of course, the full probabilistic analysis. That means to make kind of Monte Carlo simulations by defining making several analyses, in each analysis using different strength of concrete, different strength of reinforcement. And when doing this probabilistic analysis, there are two possible approaches also, one called random variables or random fields. But I don't want to go into detailed, but it is clear that with this approach, which is the most demanding, but we can actually get the information about the mean, information about the distribution, and we can then calculate the design resistance considering some probability of failure. There are other, well, one more thing coming back to this probabilistic analysis I want to note is that even though it looks very complicated, nowadays it is feasible. There are statistical approaches that can limit the number of analyses that you need to perform to, let's say, 30 even, yes? Which is feasible even with nonlinear analysis. Now, global safety factor, which would be the easiest way how to do it and the most natural. That means we calculate the mean behavior of the mean resistance of our structure, and then we apply some safety factor to come up with some design resistance. And this would be, of course, also quite natural extension of the current way of working. Of course, when we do it, we have to realize that we have no information about the distribution. It could be that there might be a problem, that the distribution of our structure is totally different from what was assumed when formulating this safety factor. Or a partial safety factor approach, where, of course, we don't know anything about the mean. We also don't know anything about the statistical distribution. Now, when I'm talking here about the partial safety factor, please don't get it confused with the classical approach. Here we call it partial safety factor, but that means when calculating this design resistance, we make nonlinear analysis as input parameters into the nonlinear analysis. We use the design values of material parameters. That means we multiply the compressive strength of concrete by the partial safety factor. Same thing for the steel and so on. And we can say that the resistance calculated in this way, we can consider it to be an estimate of the design resistance. How accurate it is, that may be a question. There are, of course, some theoretical arguments that it may not be always on the safe side. But that's what I would like to show in subsequent examples, that so far we haven't discovered a case. But doesn't mean that such a situation doesn't exist. And we have one more method, which is also included in the FIB model code, which is already introducing a little bit the probabilistic aspects. And we call it Ecole, estimate of coefficient of variation. And in this method, we make two analyses. One using average properties, and this we consider to give an estimate of the mean resistance. And then another analysis using characteristic values. And we consider this to be an estimate of the characteristic resistance. And if you do that, and we make assumptions that the distribution of resistance is log normal, which is quite realistic and accepted by almost everybody. It is then possible to make an assumption of the coefficient of variation. Then based on that, it is possible to calculate the global safety factor, considering the beta reliability index, which has been mentioned many times during this conference and also during this workshop. So it allows us to consider the probabilistic aspects or give some probabilistic input data. Nice thing is that by making one analysis with characteristic values and one with mean values, at least partially we get some sensitivity to the concrete strength and to the reinforcement strength. Because the concrete strength typically varies much more, while the difference between the characteristic and mean strength of reinforcement is not much difference. So, and when we have that, we can then really, from the mean value of resistance, calculate the design value. There is one more approach, which comes from Eurocodes, which also is nice in the sense that only one analysis is necessary. This analysis is calculated, so to speak, mean value, but it is not really mean value, because to calculate this resistance, we use mean values for reinforcement, but values for concrete are not mean, as you see here. They are even lower than the characteristic one. But in this way, it is possible to introduce the heterogeneity, the higher heterogeneity of the concrete with respect to the reinforcement, and then to have a single value of the global factor. On the other hand, this global factor is quite low, I must say. I would be a little bit afraid to design a building using nonlinear analysis only with this safety factor. But what we did, we evaluated, and I want to show you this summary of this study. We checked all these 4 safety formats on some examples which we like to think cover kind of the range of typical problems in reinforced concrete design. So starting from a simple beam which is dominated by bending, shear wall, bridge pier, which includes some secondary effects due to large deformations. This is a bridge which was tested up to failure in Sweden, so we also use it as a reference example because we have some information about the true strength. Another examples, again, shear beams. We have several shear beam examples, actually 3, because shear is a very critical behavior in reinforced concrete structures. So these are beams tested at Toronto, some with reinforcement and some even without reinforcement, without shear reinforcement, and very high beams. You see they are 2 meters high. So the size effect very much comes to place, needs to be considered. Here's an example of the behavior for these beams. I think this is with the shear reinforcement, and this one was without the shear reinforcement, yes? Here are some results from the calculation, comparison of the failure pattern. And this shows, just to give you an information of this probabilistic approach. So when we make the probabilistic approach, in this case we are using the random variables method. That means we prepare statistical inputs, but for each beam there is a single value of compressive strength or single value of tensile strength. So each beam has same properties, but different set of properties are created for different beams. We have some statistical tools for that, which are based on random sampling by Latin hypercube method. And now, just to give you an idea about the results, I have selected the most critical case, where we see the highest differences from the, let's say, standard design formulas. But that's because that's the deep shear beam from Toronto without shear reinforcement. Probably no one will design such a beam without shear reinforcement. But you see here the statistical distribution obtained from the probabilistic analysis, and here you see the results. So that method where we use the partial PSF means the partial safety method. That is the method when we use material design parameters with the safety factors in the nonlinear analysis. So this gives this 213 design resistance using the Eurocode, this value, using this coefficient of variation approach where we have two analyses. We are somewhere here. Then the probabilistic approach was somewhere here. This was the characteristic value from the probabilistic approach. Here was the mean value from the probabilistic approach. Here is the experiment. So as you can see, one always has to be a little bit, understand that usually the experiments that we have are not the mean. And for these cases, they don't make so many experiments because it's important. So they made 3 experiments. So still probably it is not the true mean. What is interesting that here would be the Eurocode formula, and here would be the ACI formula. So it definitely stops working for these large beams where the size effect is important. And now the summary, this table summarizes all the results from these, how many? 6 examples. We have actually extended this table. I was showing it during the conference also for some fiber reinforced concrete. And what you can see, this table, first of all, to understand what it is. So these are the individual, each row is the individual example. Each column is the method, those 4 methods that I was mentioning. And it is normalized with respect to the probabilistic approach. Because we can say that the probabilistic approach is the most correct one. Also, what I want to point out is it very much depends how you make the probabilistic approach. Because as it was pointed out by previous speakers, if you do probabilistic analysis, it very much depends what kind of distribution you consider for the material parameters. So when developing the probabilistic approach, what we did is that when defining the statistical distribution for instance, for the compressive strength, we used normal distribution, which kind of, I think, is used in the code, and we selected it such that it goes through the mean and it goes through the characteristic strength. So try to be as close as possible as would be the standard approach taken in the, or assumed in the code. But then I think for resistance, it's also important that with our method we have to make an assumption about the distribution of resistance, and there we used log normal distribution. So what we're looking at this, what was surprising to us is that there is no difference. I would say there is no difference, sort of. So there is, we cannot find any preference for either of these methods. So if there is no preference, I myself always saying, well, why then not use the simplest one and the most natural one, which would be to the engineers. And in my opinion, the most natural one to the engineers is the PSF method. The one where they make the nonlinear analysis using the partial safety factors. Because also if you think about this method, what this method is actually doing is that as you increase the load to the design level, it checks all the sections. So it actually is doing what the standard design is doing. That it is basically checking all the available sections, even those that you would not check normally. But disadvantage of this PSF approach is, for instance, that maybe it would be then difficult to use the same analysis to check the serviceability limit state, because you are using so low properties that the serviceability limit state check may be too conservative. So the other method that is favorite of mine is this one from Eurocode, where you can almost then have single analysis, and use it to check both ultimate as well as the serviceability limit state. Other aspect is the model uncertainty, which so far is should be encountered, and so far there are some provisions in the model code, in the probabilistic model code, as it was mentioned by Professor Mancini in the morning. There are some values going from 1 to 1.1, which is probably too low, and there is some more work that should be done here. Right now, our approach here, or our suggestions for engineers, is to make this benchmark, to analyze some benchmark cases, shear problems, bending problems, to get a confidence in your model. Okay, so I think I will conclude here. I think also I more or less summarized the conclusions already. I would say the most accurate method would be the probabilistic one. The ECOF would be the second method, which already introduces some probabilistic approaches, but it is probably still a little bit more demanding, so it will be used probably really in some most extreme situations or for some safety critical structures. And otherwise, this PSF method or this Eurocode method are the most suitable one. The PSF method has an advantage also that you can quite easily explain it to any certifying body. If you need to have your analysis certified by some independent authority, it's easy to explain them. Yes, I'm using the partial safety factor for compressive strength, and while this Eurocode one is already starting to be a little bit more complicated for them. So thank you for your attention, and of course, if there are any questions, I will be happy to answer them.
Yeah, totally 2 questions I have. One is that once we carry out this nonlinear finite element analysis, then second order effects like slenderness effects and all we need not consider separately, I suppose. If you can please confirm.
I'm sorry, you?
Second order effects,
yes,
like slenderness effects and all that, which we otherwise add on as additional bending moments, etc. I suppose they are not required to be carried out separately, because this will be automatically built into the analysis that we carry out. Is that right?
Yes, usually any nonlinear finite element code which can handle material nonlinearity can also consider large deformations. So it is not a problem to automatically include it in the analysis.
Right. Other thing is, you mentioned that you have to go on increasing the loads for the failure to arrive, and then you work out that you know the design loadings or the factors, and you get the safety factors, and therefore you determine whether the structure is safe or not.
Yes.
So for this, I think you have to first define your limits when you say it's failure. For each element, the limits of failure would be different. It could be a limit of maybe cracking, or maybe deflections, or maybe, I don't know, something else. So can you just throw some light on this?
Yes, this is an important question or important issue. You are right. Well, typically when we do this kind of analysis, as a failure we consider really the collapse. So as you see here, we keep increasing the load until we really see that the load does not increase anymore, it is going down. So of course you need to have some special nonlinear solution techniques to be able to go into post-peak. But on the other hand, from practical point of view, very often you can also have a different criteria. That you say that the deformations are so big, or that the strains maybe in the tendons are so large that there will be a rupture of tendons, so you can consider that as a peak load or as a failure load. But you really should be careful in this, that what you consider as a failure load is really some kind of meaningful failure load. If it is not just some side effect of your analysis, let's say. Yes.
One question, sir. in the methods which we have used, it's not necessary to have any kind of prior knowledge about what is likely to happen. Because what will happen will be brought out by the analysis itself. But in a design offices, there could be, I am saying could be, a more simplified approach, and that is to try to identify the type of failures, mechanisms, which may lead to a failure, and you don't know which one will lead to a failure. In which case, what one could do is, if you are, say, calculating the failure of a beam by bending of the reinforcement, because normally we design under reinforced sections, not the over reinforced sections. So we know that the critical, this mode failure will be governed by the steel failure. In which case it is simpler to assume the steel at the characteristic level. We know the actual steel is higher than that. But assume it to be the characteristic level and let all other elements to be chosen randomly wherever they fall to. I mean, they will not necessarily be at the mean value or the lower value or wherever they fall to be, and make few trials like that, and then you know that if it fails by reinforcement stressing, then the failure load is some X value. Then you do the analysis that in spite of all that what I was saying, maybe there are effects in the structure which I can't understand because the structure is indeterminate nature and the exact strains and forces are unknown, in which case I say, okay, let it be failed by the concrete strength, crushing. And then hold the concrete only at the characteristics value, lowest value, and let all of this by the statistical method choose at random. Now, if you can do such 2 or 3 analyses, will it, at least I understand it by physical feel more than what is happening, instead of using these sort of black box methods.
Well, I don't know what you mean by black box methods. Yes,
black box
because,
is simply, sir. No, I will
if
tell
you
you.
Think about it in this way.
I will tell you what I mean.
You are using is also a black box.
Sir, if you are using the plate element or something, it doesn't use all. It uses only few degrees of freedom. It's not a real estimate of what happens. Therefore, a bending analysis which is quite correctly producing bending moments or something using one type of element is not necessarily representing the other effects quite effectively. And in that sense, mathematics is inadequate.
For bending elements?
It gives only particular that type of solution.
Yes. That's why I was mentioning.
Sir, in the old days, the greatest challenge was to choose the right kind of element to describe your structure. And I have known the plate and shell element structures, deep structures, being used by the wrong element and coming to totally wrong results.
Yeah, that's always the danger when using finite element analysis. This danger doesn't matter if you are using linear or nonlinear. This problem is always there that somebody is using wrong elements. And your question or your comment, if I understood it correctly, about the beam elements or bending elements, that they not capture the reality. That's why I was also mentioning that for some of these critical situations, we distinguish that we use bending elements in the area where bending is the dominant, and in the areas where shear may be the dominant problem, there it is better to use solid elements.
That's what I meant, yeah.
Of course, the model becomes more complicated.
There's also the issue of compatibility and condensing at the nodes and all that will arise. That's obvious. So choosing the element from the library is to almost know what you want to see as failure modes. So you choose the elements which can model that failure mode in that region. Is that what you're saying? That's the point, isn't it?
That's right. But on the other hand, this, of course, depends always on the engineer using the tool. Yeah. If the engineer is, let's say, good and understand what he's doing, then he should be able also to detect that, let's say, he's used bending elements, but even the bending elements calculate shear.
Yes.
And then when he could see that the shear in some regions of his model are becoming a little bit higher, then
He
maybe
switched to brick.
then it is safe. Then he should somehow either make separate checks in these regions or make the refinement there and use a different element.
Yeah. And the other point I was just thinking, long ago, there used to be something called a quarter point collapse on the shell element to model fracture problems and things. I don't know if it's still being used.
What do you mean?
On the shell element, quarter point collapse, to model the crack directionality, and that used to be a specific technique which we used to use in ANSYS and LUSAS and all in the old days.
Yes, this is
I don't know if it's still being used or it's outdated.
No, this is a technique which was typically used to model linear elastic fracture mechanics, propagation, stress singularity at the crack tip, to use higher order elements and then put the middle point to a quarter point position, which then automatically introduces the stress singularity there. We don't use this approach for two reasons. First of all, linear elastic fracture mechanics is not considered that suitable for concrete, because there is usually a quite large process zone where the cohesive stresses are gradually dissipated. So, yeah, this is a standard approach to modeling cracks. But in reinforced concrete, there are usually so many cracks, so many micro cracks, that to model each crack by this technique would be too demanding.